Hey, there should be some interesting things here that you may be familiar with. Parametric equations and calculus. And this is the first in a series. And both of those things you've seen before, I think. Parametric equations, here we are up here. Parametric equations. We were just doing those in relationship to intersection of planes and parameters in the vector form of the straight line. And calculus, of course. Newton and Leibniz discovered calculus about the same time and slightly different approaches. And I think this summary over here, or this summarises pretty much what they were about. In other words, having B1 approach B4 and the limiting position of that chord being tangency, which they defined as the instantaneous rate of change of some function. And those functions were all written as y in terms of x, explicit functions. Well, it's explicit when you spell out exactly the dependence of the function on a single variable there. Parametric equations, of course, are different than that, and we'll come and look at that in a minute. But what about this little bundle over here? I don't know whether you've seen some earlier presentations in Huddy Maths, but there's one for a subject called Math Studies, where I call this Huddy's trichotomy. 3 different ways of thinking about the derivative, what you get from the process of differentiation, dy by dx, we say that, or the derived function f dash x, either of those two. That's the derivative, and the trichotomy says it could mean the slope of the tangent or instantaneous velocity, either any of those. So when you think of the derivative or any of those things, you should think of the other two. It's a trichotomy because in different circumstances, various circumstances, it's good to think of the derivative in any of those ways. I wonder, just a little aside here, dy by dx. Do you know where that came from? What are the d's doing in there? dy by dx. It's not d times y divided by d times x, is it? It's a much more meaningful expression than that. And I'll just show you here. It's the limit as delta x tends to naught of delta y over delta x. Don't know whether you realise, but delta in maths is equivalent to change in. We use it quite a bit instead of change in. So this is change in y over change in x. This is the slope of the chord. And we take the limit as delta x tends to naught. Come over here, it's this movement here again, coming down there. And we're calling the slope of a chord change in y over change in x and finding the limiting position of that. Now, I don't know whether you knew that, but this is a Greek capital for D. And that's where the D comes from. Interesting stuff, isn't it? Math symbols always have very important origins and are symbolic of where they come from. Okay, so that's that little one there. And of course this is meaning the derived function f dash x, which is derived from f of x by that limit theory. Okay, well there's calculus, or a little bit of a touch up on calculus here. What is a parameter? Okay, let's go down here to the equation of a line in 3 dimensions here. And you can say we had this parameter t, was, if you like, another property or a variable within the system. In at this stage, when we were doing this, in 3D space, we were not connecting x, y and z. We were connecting to each other, as we do in the Cartesian form. We were connecting each of the x, y and z's to a parameter, t, which they shared. And t, if you like, was what was the Huddyism there. You start at this point and t times the direction vector. T times the direction vector, which here would have been a, b, c. Remember that? Okay, so if you like, the property of the system to get to your general point, x, y, z, the property of the system was the t representing the multiples, if you like, or lots of the direction vector to get out to that particular point. So we were relating these not so much to each other then, but to the other property of the system, which was t. Okay, so look out, here it comes. Here it comes. This is calculus and parametrics united here. So would it be possible to find dx by dt? Well, hang on, let's go back up to Hutty's trichotomy here. Instantaneous rate of change. The rate of change of a function with respect to a variable. Yes, it could be. This would be the rate of change of x compared to t, thinking of x as a function in t instead of y as a function in x. Just step across and think of it generically. Well, in general, what we're doing with calculus, we're finding here the rate of change of y with respect to t. And down here, how quickly z is changing with respect to t. So this idea of calculus is very, very important. And please think of it in general terms, not just y as some function in x. Okay, so that's where the thinking has to start. So come down and let's have a look. I've got something here for you. So what do these mean? Okay, so what do these mean? We've just had a look at it. Means the rate of change of x with respect to t, rate of change of x with respect to t, is a. Okay, so as t changes by 1 unit, x would change by a units, and a could be positive or negative there. Same thing, rate of change of y with respect to x, and rate of change of z with respect of y with respect to t, and rate of change of z with respect to t. All right, and we're going to look at whether functions change uniformly or regularly or not. So let's have a look now at a little excerpt here that I've got from Hayes and Harris publications. So you should get their book there and have a look. I think this is a definitive way of having an introduction to parametric equations. Okay, so what I'd like you to try to do is to do this investigation, and I'm going to do each part, sorry about that, get rid of that, each part of that investigation so that you can have a look. Okay, yacht has a position, a two-dimensional problem here. The yacht's not going up and down, well, unless there's a lot of waves, mate. But anyway, we're just considering it in 2D space here, and another yacht, and they've got velocity vectors, and what we're going to do is plot the path and investigate this motion. Okay, the plot of the two yachts, and it's going to be on the Cartesian plane, isn't it? But what we're going to do is try to accommodate that movement, not as y in terms of x on the Cartesian plane, but in terms of the velocity vector. All right, so I want you to pause the presentation and try to do these parts. Okay, so there's 7 parts there. So see what you think. And I'm going to now show you the answers. It's very important that you, even if you feel confident with the work, that you do watch what I'm doing and listen to the ideas. Okay, here we go. Let's have a look at it. Okay, so here we are. I've got a Cartesian system here. Yacht has initial position neg 10, 4, so that's there. That's the yacht A is there. And has a velocity vector 2, neg 1. So if we start there, in 1 unit in time we'll go 2, neg 1. So it would then be there. Okay, get that one, the velocity vector is 2, neg 1. So 1 unit in time, let's call it A1, would be there. Now yacht B is position 3, neg 13. So it's down here somewhere. That's yacht B. And it's got velocity vector neg 1, so come across neg 1 and 3. Up there. So after 1 unit in time, it would have gone to there, and we call that maybe B1. So this one would have gone up, hang on, go back up to A, would have gone to there. Okay, bit hard to write on the screen. So it certainly looks like an interesting problem. Now we're not describing the movement of A and B in terms of y and x here directly. Okay, let's have a look at going on with it. So we've got that. Now, explain why the position of each yacht at time t is given by this. I just remember where we are. So this is neg 10, 4. So that's yacht A. And this one over here is 3 neg 13, yacht B. Okay, now let's try to use a vector equation now. So we're going to say, right, now, yacht A, so this would be out there. Yacht A is there at the moment. So to get to yacht A, this is a vector neg 10, 4 from the origin. And then every time interval, now we're going to cross over here. So every time interval, it's going to go across 2 and down 1. Okay, so we have a direction vector now down here somewhere. And every time unit, it goes at 2 neg 1. So after a period of time, if we call t time, it would be what? We travel out to the point A here, RA, the vector to go to the new position of A, would be travel out to the point from the origin plus t times the velocity vector. If this is the velocity vector, then this must be units in time. Okay, so here we're saying, yes, that fits as long as t is time. And we could say the same for B here. To get to the point B, R of B, these are vectors, bold there, you travel out to the point 3 neg 13, and then the growth factor, if you like, is t lots of neg 1, 3. Why is it neg 1, 3? Well, this is a velocity vector, and if we say every unit in time, it's going to travel that distance, neg 1 in the x and 3 in the y, then that works, doesn't it? It's the idea of vector equations with now t not just being any parameter, it's actually going to stand for time. And that's why we're multiplying the time by the velocity vector. Interesting application, isn't it? Okay, so let's keep going and let's have a look at what we've got. Okay. So on square paper, plot the path of yachts when t equals 0. Okay, well this was neg 10, hang on, what was it? Let's just go back and have a look. It was neg 10, 4 and 3 neg 13. Neg 10, 4 and 3 neg 13. Okay, and this is going to 1, 2 neg 1, so that's A0, A1, 2 neg 1, A2, 2 neg 1, A3, 2 neg 1, A4, 2 neg 1, A5. Ah, it's a straight line. I wonder if you know why it's a straight line. Okay, constant outer or constant slope, something like that. Let's have a look. All of those things, I think. Okay, what makes a line straight? Oh, constant gradient, constant slope. Would this have a constant slope? And what would that slope be? Okay, you might think about that. Now this one, what's this one doing? Neg 1, 3. So it's going neg 1, 3. So this is B0, B1, then neg 1, 3, B2, neg 1, 3, B3, and neg 1, 3, B4, neg 1, 3, B5. Hang on, we've got that right. Neg 1, 3, yep, that looks right. Okay, so that also should be a straight line. We're moving across and up the same amount each time across, oops, messed that one up. So we have, hang on, let's just check this one. Neg 1, 3 shouldn't have been there. Neg 1, 3 should be there. And neg 1, 3 should be there. Okay. Neg 1, 3. Very good. So this is B4 and neg 1, 3 up here, B5. Okay. So it is the same each time. Neg 1, 3 and neg 1, 3 and so on. So again, the path is straight for both of them because we have a constant gradient. I don't know what is that gradient for yacht A. Let's put it down in the old Cartesian form. Slope for yacht A, y step over x step. Remember, neg 1 is the y step. The velocity vector is 2 neg 1. That's x component, y component. So what's that? And the slope of this yacht B's straight line path here is going to be neg 13, what was it, 3, neg 1, 3, so 3 over neg 1, or neg 3. Okay, so just remember there, the velocity vector was neg 1, 3, y step over x step there. Just don't confuse those two. So it looks like they cross over, the paths cross. But what can you say? What can you say here? At B4, there's the yacht B, or that B4 represents the yacht B at 4 time units. There's A4. So here we are. There. They cross over, but do they cross over at the same point in time to get a collision? Can you see the parameter coming in? It's not just about y and x and whether they intersect. We have for all another property of the system. This is the idea of parametrics. You've got the y and x relationships producing these straight lines. Okay, and then you've got when will they be at this point of intersection somewhere up here where these paths cross. Would it be at the same point in time? Hang on, I think I got that wrong again. Let's get rid of this. So here, B's line. Lost that. Okay, so here's A's line coming through here, and B. I've got problems here now. Is there? So it's going through. Right, that's somewhere hard to write on the screen. So here, this point of intersection is a common point for those two paths. But at what time? Okay, you get the idea of this other property of the system. This is a good example to get your head around the idea of a parametric variable here. All right, so come down and let's do the next bit. Find the position vector of B relative to A. That's A to B. So if we had points A and B, we could work it out. X coordinate of the second minus x coordinate of the first. Y coordinate of the second minus y coordinate of the first. Going from A to B. Okay, well, can we do it? Do you remember from the last presentation on vector and vector equation of lines and planes, we used parametric form? So here we could say here x of A is neg 10 plus 2t, and y of A is 4 take t, remember that? And over here, x of B is 3 take t, y of B equals neg 13 plus 3t. So, the general position of point A on this journey, on this sailing boat, is neg 10 plus 2t. We can't specify it as a single point. Okay, we can say this, and we can say the general point on yacht A's path is that. And remember, t is common here. T is time. and we're saying that they start off, just remember, they start at the same time. Okay, otherwise you can't share that parameter between the two lines. They start at the same time. So what would the general vector AB look like? The general vector AB would be the x of A minus x of B minus the x of A, okay, comma, the y of B, second point, minus the first, minus neg 4 take t. Okay, so that's the point there. Oops, and I made a mistake already. 4, I've copied that down incorrectly. It's 4 take t, and over here 4 take t. Yep, just watch that. Okay, so that's interesting what we've got there in terms of a parametric form for the vector A, for the vector AB, and we're going to use points, general points A and B on the two paths. Okay, so let's simplify this. So 3 take neg 10 is 3 plus 10 is 13. And neg t take 2t, neg 3t. Then oops, in the second part there, we've got neg 13 take 4, neg 17, 3t take neg is plus, so that's 4t. Okay, and now what we want to do, that's it, that's our vector AB. I think in the next part we need to do some work with it. So, how are you going? Get the idea of parametrics there. So let's just go down a bit now and see what else they want us to do. Oh, use 3 to show the distance. So I better write down here, AB would be the general vector between the two, and its length would be the general distance between the lines. And they want us to find d squared because it's easier to do. So d squared would be the length of AB squared, wouldn't it? D, the distance between the yachts, distance between the general point on yacht A's path and the general point on yacht B's path. So squaring it, remember the distance here, square root of x2 take x1 squared plus y2 take y1 squared. So all we have to do is don't want the square root, we're just going to square these. These are the x2 take x1 that we just did here. Okay, so this is 13 take 3t squared plus neg 17 plus 4t squared, which is whatever, 169. Take whatever, what is this? So a 2AB here is 78. Take 78t plus 9t squared. And now we've got plus, now neg 17 times 17. Neg 17 times neg 17 is positive. And what is that? 289, is it? Is that right? 189, what do you reckon? I think it's 189 take 126t plus 16t squared. Should be using a calculator for this, but there you are, we've got that. And let's have a go now at doing it. Okay, hang on, I was playing around with you, and it should be 289. Okay, so here we are. So what we've got here is 9t squared plus 16t squared is 25t squared, and then neg 78t, and here neg 126t is neg 214t, and then we've got 169 and 289 is 458. Okay, just check that, 458. All right, so d squared is that, and we should put, because it's show as required. All right, so yes, interesting, isn't it? So now we've got an expression for the square of the distance between them. At any point in time t, we can tell how far apart the yachts are. All right, come down and let's have a look. Show that this is a minimum when t equals 4.28. Well, you might think about that. What are the two ways you can show this is a minimum? Well, I think you could use calculus. Let's find the derivative of d squared with respect to t. And that would be 50t, using the x to the n rule, take 214. And then we can say max or min occur when the derivative is 0. So let's put this equal to 0, and we get 50t, equals 214, work more slowly than this. This is 214 over 50, which is 4.28. Okay, as required. Okay, so that would be one way, and we should check that it's a max, that it's a min, sorry. Check minimum since a is greater than 0 in the quadratic. Okay, in other words, it's like that, isn't it? Or we could use a sign diagram, or we could use a second derivative. Let's just, for a matter of interest, do the second derivative. So the second derivative, d2 d squared by dt, the second derivative would be 50, which is greater than 0, which implies a local minimum. Okay, or a sign diagram. Do any of those ways, but you should just confirm that the 0 position is a minimum, because it could be a max or a min, any turning point. Remember the calculus stuff there. What's another way of doing it? Well, we can't use technology because it says show that. So you can't just draw a graph and take it from there. You could use quadratic theory. T equals neg b over 2a is the turning point of any quadratic, and that equals 214 over 50, which equals 4.28 as required. You are allowed to use that, and since a is greater than 0 in the quadratic, it is a minimum. Something like that. Okay, so you must validate that it's a minimum. All right, so we've done that. So at 4.28, that agrees with our plot pretty well, doesn't it? They were crossing over it between 4 and 5 seconds there, 4 and 5 time units, whatever they were, and this was the distance. So at that point in time, that was their closest. So they actually never got to 0 position to collide, as we suspected they wouldn't. They didn't actually collide there. Okay, so at 4.28 they came closest to each other. Okay, well, let's go on and have a look. Hence find the time when d is a minimum. I've got that there, d is 2.1. Okay, so here, when d is a minimum, the d a minimum, when d squared is going to be a minimum, because it can't be plus or minus, so d is greater than 0. So because d is a positive, it's a distance, then it's going to be a minimum when it squares the minimum, or vice versa. So the minimum at d equals 4.28. So now we're going to have to find d squared equals, what was it, 25, hang on, we'll have to go back up and pinch it from up here. 25t squared, take 214t, I should have put this down, plus 458. Just check that, hang on. Take 214, I've got those on the right. Take 214t plus 458. So now we're going to substitute in 4.28. So 4.28, need a calculator for this. Take 214 by 4.28 plus 458. Okay, and if you do that on the calculator, you can do it in one entry, all of that down here. And I think you get 0.2, whatever the units are for distance there. Okay, so that's just a little bit of calculator work there, using technology. All right, so we don't know the time or distance units here. All right, so getting the hang of this, very important use of parametric equations for a general point on lines or bars, for a general point. Okay, and use that. Okay, let's come down and have a look at the last bit here. Investigate other situations with different initial position and velocity vectors. You should be able to create a situation where the yachts will collide. Well, let's go out to where yacht A was, that was A, and let's keep its velocity, 2 neg 1, so that's its first point after t equals 1, and then 3 neg 13, if we come down here again, we'll start yacht B at the same point, but let's make them collide. That's a bit cruel. So let's say, where is yacht A at t equals 5? So the position of the yacht is neg 10, 4 plus 5 lots of t neg 1, which is a neg 10 plus 10. We position 0, oops, it's a vector, so going to be 0, and 4 take 5 is neg 1. So that is the point A at that time, A5, is 0 neg 1. So that's there as it was before. Let's come over here and construct this now. At t is 5, what we want is the vector RA will be 3 neg 13 plus 5 times something or other. We're going to give it a velocity vector so it ends up at the same point at the same time. Okay, call it P and Q. So 3 must be 5P. Hang on. 3 plus 5P must equal 0. And neg 13 plus 5Q must equal neg 1, because it's a point 0 neg 1. We want them both to be there at 5 seconds, 5 time units, whatever. So here 5p equals neg 3, p is neg 3/5, and over here adding 13 to both sides, 5q equals 12, q is 12 over 5. Okay, so what does that mean? If we give yacht B a velocity vector equal to neg 3/5 and 12/5 in 5 time units, it will be at this same point. So what we've got to do is neg 3/5, hard to plot that, and 12/5 somewhere up here, and then it will collide after 5 of those. 1, 2, 3, roughly 4, 5. If this vector is neg 3/5 and 12/5. So you get the idea. We've manufactured, and of course there's an infinite number of possibilities. You could start the yachts at different points as well, and so on. You can play with that. All right, are you getting the idea of bringing in that thought about the dependence of the position and the point on the Cartesian plane here, which is being guided or related to another property, in this case time. Okay, come down and let's formalise some of this stuff now, and we were going to look at Hayes' version of this, which is pairs of uniformly varying quantities. Let's just review the idea of vector equation. You travel out to a point on a line, and then it's t times a direction vector to get to a point. Whoa, we haven't seen this before, x of t, y of t. We're saying the position of that point depends upon the parameter's value t, which we know. And so OP equals OA plus AP, and that's what we've got. Let's have a look then at this parametric form now. So the position of the general point, travel out to a known point on the line, there it is, it's a vector, so travelling out from the origin plus t times the direction vector, where t is any variable. And here we're saying it's greater than or equal to 0 for this discussion. Okay, so we're going up this way. All right, so here let's have a look at what we can say. Well, first of all, if we have that, we can split it into parametric equations. X of t equals x naught plus ta. Y of t equals y naught plus tb. Parametric equations. Now, if time is a variable, so let's differentiate this and this with respect to time. X dash t, that's a constant, so the derivative of this function with respect to time is the constant, x to the n rule, so it's a, and the derivative of this function with respect to time, that's a constant with respect to time, and so this is b. So x dash t is a and y dash t is b as the rate of change of these two parametric forms here. And so what do you notice? X prime t is the x component of velocity vector and y prime t is the y component of a velocity vector, because that vector x prime t, y prime t, okay, that is the rate of change of the movement in the x direction and the movement in the y direction. All right, so let's just bring that together a bit now. So therefore, we've just indicated that the velocity vector is AB and it's constant for that moving point. That's why it's moving in a straight line. Both of them had fixed velocity vectors, so every time unit goes A in the x and B in the y. And so both of them were following straight lines, and they are therefore said to have uniform velocity, because both of those were constant vectors. Okay, so x prime t and y prime t for both of the boats were constant values. So we call that a pair of uniformly varying quantities. Right? The change in x and the change in y were both uniform because they didn't depend upon time. Every time unit went by, it went, take dot A, 2 in the x and neg 1 in the y. And this were constant for t. Okay, so that pair of quantities varying, the x movement and the y movement, are called uniformly varying quantities because their rate of change with respect to time was constant. You get the idea? Hope it's coming together for you. Okay, let's have a look at doing a problem here. Okay, so a particle moves and then we have parametric equations for it, and t is in seconds here, so we are going to use a time variable on our plot and not just a general parameter t. Okay, distance in, oops, hang on, sorry about that. Distance is in meters and time is in seconds. Find the initial position of p. So that initial always means t is naught. So sub t is naught in both of these, and you get 2, 4. Okay, find the x and y components of the velocity vector. What will the velocity vector be? Velocity vector b would be the rate of change of the x displacement with time and the y displacement with time. So here it is, the derivative of that is neg 3, derivative of that is 2. Okay, so velocity vector, use the bracket for velocity, is that. Illustrate the motion showing points where t is naught, so you just sub naught in, 1 in, 2 in and 3 in, to the forms up here, the parametric forms. Okay, so here, what would you have expected? Well, we've got velocity vector -3 and 2, so coming down, let's look at that graph. Here we go -3 and up 2, -3 and up 2. So if you wanted to just keep overlapping with the coordinate geometry, not with just the parametrics now, the velocity vector is -3, 2. So in coordinate geometry land, the slope of that line is 2 over -3. Just compare it back the other way there, 2 over -3. And you could still find the coordinate, the equation of the line with coordinate geometry, y equals mx plus c idea. And there's our slope. So keep remembering all the stuff that went before. That's important because they are other skills you can bring to any problem. All right, let's have a look. Here we are, x step is -3, y step is 2. And what we were going to find was to find, hang on, I just didn't read that question, did I? So let's come back up here a bit. Comment on the speed of p. Okay, so the speed, 3 in this direction, 2, so the size of that velocity vector, remember the size of the vector -3, 2 is the square root of the x component squared plus the y component squared. That's what they're saying here. So it's root 13 meters per second, which is the length of the velocity vector. So that's the speed, the size of the velocity, which you would have had in other calculus studies that you've done. You need to have that here for this course. All right, let's go and do some. So here are some little problems for you. Question, there's only 3, but I want you to study them carefully because they are important in understanding parametrics. So question 1 and 2, pause it and have a go, and I'll show you the answers in a minute. And question 3. All right, let's go and have a look at the answers. The most important thing here is to get your head around the idea of the dependence of x and y, in this case on 2D space, being related to another property of the system, in most of these cases here now, time. All right, come down to question 2, and I'll bring up part E in a minute. Let's see if we can get it all on there. I can't. There's E, the last bit of E for 2, and question 3. Just come down a little bit. Let's see if we can finish this off. Okay. I think the torpedo problem here is interesting. Fair bit of work there. Just remembering that if you have two different lines, if you're going to use a common T, if you're going to use T in both, it must be starting at the same time and all that stuff. Okay, because otherwise you might have to say it's got a difference there between T in one and T in the other. Just have a look at some of those. Okay. All right, so I hope you found that an interesting introduction to parametrics and calculus, and we've got our first pair of uniformly varying quantities. Remember, because their rates of change with respect to time were constant. Okay. Well, I look forward to seeing you in the next presentation. Cheers for now.